No, all good. Today we're going to talk about data security, which is somewhat related to the inheriting or using some of the concepts we've used and discussed in the last 2 weeks. And we're going to do the exercises jointly between data security and access control from what we had this Monday. Learning goals for this class is understand how access control and encryption are applied in data security, as in combining these two classes. Learning methods of secure password storage and techniques for password cracking. Also understanding how the limitations of these cracking techniques are, both regarding storage and computational limitations, and then know some basics of secure remote password protocols. Data storage requirements are ubiquitous. Like one of the reasons why we are doing working in computers, because it managed or allowed us to store lots of data. And there's pretty much any kind of application you will use will store some data of you, the customer, or you as a user, along with a lot of other data that is being collected throughout the system or the need for the application. So for banking, industry, social networks, government, research, mobile applications, all of them share different kinds of data requirements. There's lots of new and massive amounts of data storages that are being accumulated, which resulted in these interesting new trends called big data. Like there was the hype trend from 10 years ago, and now machine learning, that's a new hype trend. Now we've amassed all of this data, we're throwing some of the additional compute that we've gathered over the last couple of years in it and trying to get additional meaning out of this data. But then companies also must consider the security of the data that they store. As a company, if you're storing data, you're certainly responsible for this data, and you have a moral definitely, but also a legal obligation to actually take care of the data, especially if it is about users. In Europe, we have GDPR and other data laws that limit the amount of data that you can process. It also gives users rights in how they can handle their data. Now, there's interesting questions that you need to ask yourself as a software developer or as a company. Like, for example, what are the security requirements that we want to distill into our project? What are the main attack vectors that we have to protect against, especially as we're building larger and complex applications for data management? Also, what are the main protections of database systems? This is not a database class, so we're not going to cover databases in detail, but we're just covering how you can actually enforce security principles on databases and how to handle data in itself. We're a bit agnostic regarding the underlying storage, so we don't talk too much about SQL servers or other kind of data storage servers, but we're trying to be a bit agnostic to all the different techniques. Now, in a classic setup, we have some form of database. This can be a set of flat files. This can be a single file. This can be an actual database server with terabytes or petabytes of data, and then some kind of application development or application that is running the front of it, where users can access the database through that. There's different users that are going through the internet, and usually this goes through some form of firewall limiting the amount of access that these users have. There's different layers of the application that does user management, authentication, authorization, and whatnot, limiting the different parts of the data that can be accessed, filtered at all the different levels. So immediately we see here network level access at the firewall, access restrictions at the application level, authentication at the application level, and then also other aspects at the database layer. Right? Now, what is missing here on this slide is one of the recent developments that we moved to the cloud. If you look at cloud services or platform as a service approaches, they're pretty similar, except that companies have given up all form of control over their data and placement, where it's being moved and whatnot. Now everything is in the in the cloud. Right? Now, as we're looking at this, and if you think back about the class on Monday, which should still be somewhere present, we discussed this from a very simple approach, right? It was just a compute system, a user working on the system. But in any real environment, in any real deployment, we've got a lot of different layers that we have to take care of. And this is where different kind of multi-tier architectures come in. And there's, for example, the presentation tier that just displays the different aspects to the users, to the different customers or whatnot. Because it just takes the data and kind of highlights it. So it's the level, the part of the application that is closest to the actual user and the main interface. There's application or logic tier that does all the compute with the data, as in this describes the logic or how this is being handled, and the data tier that just stores all the information. As there's 3 different tiers for the German-speaking ones in the room, these are different nice animals. So we have the clever animal that remembers everything, which is the elephant, the intelligent animal that does the logic and the compute, and we've got the beautiful animal out there, the peacock, that displays all your data. Tier in German is animal for those who don't speak German, right? So elephant remembers, octopus is clever, and then the peacock does the beautiful representation of the different aspects. This will not be a quiz question. Now, if you look at different attacks at all of these different levels, there's been a plethora of attacks against database systems, because some of the lower end databases may actually be exposed to it. Just one example of Steam, where they had an API vulnerability, which resulted in unauthenticated users being able to access CD keys for any games, downloading and cracking any of the new games that are out there. Epic Games had an issue where the raw data accounts for all Fortnite players were accessible, including such confidential data such as credit card information and whatnot, which is not great. Amadeus Group, who knows Amadeus as a company? Quick show of hands. 1. What is Amadeus? Not the composer that just dropped a new CD. Oh, another Amadeus. Yeah. Amadeus is also a company for anybody knows what Amadeus is? Has anybody taken a flight? Yes, this is booked through Amadeus. It's a back-end system that holds all the airlines together and pretty much runs the travel industry. Like any hotel bookings, flights, whatnot, this is all going through Amadeus. Interestingly, this is like a very clunky old text system where you're paying for each character that you're sending. It's also unstructured, so it's just plain text. And then different companies provide additional services by parsing this text file and then just displaying this nicely in on the websites that you actually see. So it's a fairly big company, as you can imagine, that is an interesting target. Pretty much runs the flight industry and orchestrated, like if you're buying flight tickets or whatnot, it's usually going through them. Washington State, more recently, different records were exposed for anybody who applied for unemployment benefits, right? So it's a fairly severe list of information. You see, all of these companies have quite a bit of private information available. So yeah, data is clearly worthy of being protected and needs to be protected. Which brings us to database access control. Right? We've just spent 3 hours talking about authentication and access control. What else do we need? Right? did we just talk about all of this? The reality is a bit more nuanced, right? And here we're going to look at this from the perspective of databases and how to manage this on databases. Now, what they think is different for databases compared to the stuff that we discussed on Monday. What's the same? What applies?
Give access to different people, but the difference is that there are much more users.
You're saying there's more users. That's one of the differences. What remains the same is that we have to use the same principles of authentication and authorization. Yeah, to some extent. What else? What's an additional complexity that we have to look at that we neglected a little bit so far? Yeah. Multiple people accessing the database at the same time. Yes, there's concurrency to some extent. Yes. What else?
Scale. It's much bigger. A lot more data.
More data and scale. Yes. Not just bigger, but also something else.
The database is split among multiple devices.
The database can be split among multiple devices. That too. Yeah.
The relationships between the data.
There's relationships between data, yes. How is a database server usually implemented on a large system? It is a service, right? If you think about the Unix example or the Linux example we did with a username, right? The database just runs as its own user. And it's just a program that runs as a user. And we've got access control at many different layers that we have to take care of. And each layer needs to implement proper access control. Hardware layer, right? The database is stored somewhere on a disk. And somebody could just run into the server center and steal our disk with all our data on it. Or, let's say we have a RAID, a disk fails, we trash it, and then somebody grabs this disk and recovers the data from it. Right? It's an interesting attack level. The operating system, right? As I just mentioned, the database server is just an application that runs, and somebody with root access there could access all the files that the database is stored in. The database itself, there's database administrators, right? The database has its own management with users that are orthogonal to the users that are administering the system. So we've got the hardware people taking care of hard drives. We've got the sysadmins taking care of the system itself. We've got the database administrators to take care of the database. We've got the network, right? There's the application tier somewhat interacts with the database and is sending data back and forth through potentially unencrypted TCP connections or exposed connections, even if it is connected through TLS. And then the application, right, which does another layer of user management. Right, so there's if you log into an application, if you go through the stack, you're logging in as your user to access your, I don't know, your data on Facebook or wherever, or Instagram. You want to look at a couple of pictures. You log in here, goes through the network, connects to a database. There's a user here. There's going through the application logic. You're being authenticated. You're going through the network internally. You're going through the database, connecting as a database user, which has nothing to do with you. You're going through the operating system. You're going to the actual disk on the hardware side, right? So there's all these different layers that need to authenticate and authorize each other when you access the different parts. Following the principles we had in the very first class, and also on Monday mentioned a bit, we want to enforce least privileges. So each layer should have the least amount of privileges possible. Each user at each layer should have the least amount of privileges possible. Each actor can only access the resources strictly needed for its function. Therefore, we should separate the different users. And this must be applied through all the different levels that we look at. Right? So if you look at the hardware level, hardware access control, in the end, this could be a physical machine in the data center. And for that, we need physical protection. We need to make sure that not everybody can just walk up and steal a hard drive. Right? So there's usually, who's been in a data center in the past? A few? What did you need to do to get in?
Go through secure system with some kind of fire protection. So push the button, opens the door, so the lamp turns on, and a lot of different stuff which protects from different problems.
Was there access control?
Yeah.
Which form?
It was some kind of cards. I think RFID or something like that. Yeah, and that's it.
And everybody with a card could go in?
Yep.
Were there cameras?
Yeah, also cameras.
Yeah, so likely there's cameras and cards. This is pretty normal. Sometimes you have to go through multiple doors, one after the other, just to come pro for the data center here in the IC center. Okay, yeah, it's pretty cool. There's sometimes multiple layers of security that you need to first. For example, 3 weeks ago, I was at CERN talking to the CISO. And we had a tour of the data center. There you need to go through several layers of security. First, you need to authenticate it when you enter the secure site, then when you go through the door of the building, then when you go into the server room and whatnot. So you have to authenticate 3, 4, 5 times, sometimes with fingerprints, sometimes with just a ID or whatnot that is being compared. So there's usually multiple layers of security that is being protected, right? So for physical hardware, we've got it pretty well laid out on what you need to do, right? Locks, cameras, alarms, whatnot. In addition, I think what you mentioned as well, there's this other, not just security, but also reliability and safety. What's the biggest threat to a data center?
Fire.
Fire, yes. How do you usually protect against fire?
No, yes.
Water? What does it do to the servers? How well does how well do electronics cope with water? Not so well. How do you get rid of fire? Get rid of oxygen, right? So there's like several approaches in server centers. One of the most common approaches for high security server centers is to just get rid of oxygen. Kind of sucks for humans, but it really saves the hardware. You know, like if you're a sysadmin in the center, you know where you stand in the value chain if the air is being sucked out while you're still in. That's usually why they have like dead man switches, where you get like masks and stuff not, or the fire prevention will not kick in if humans are in the server center. There's like the two most common ones are either gas, so that the room is filled with gas, like nitrogen usually, which is also not good for human. The other approach is to get rid of fire is just to get oxygen under like 16%. At around 21% oxygen, they just go to 16%, which makes fire pretty much impossible. Humans can still survive, but it feels like you're climbing Mount Everest, right? So you get a good exercise when you're carrying around servers in these rooms. So this is for safety and reliability, and for security with the access controls and whatnot. Now, but I also mentioned that we've moved a lot of the services into the cloud, right? Now, if these services are in the cloud, the only thing you need is your access token. Like if I find your access token for Hetzner, AWS, something else, like one of the big cloud providers, I can just log in, and I'm the administrator then, and I can just download your virtual machine image, and thereby steal your disk. Right? This is fairly easier, much easier, and it's a risk that is still a little bit neglected by many of the companies that are moving into the cloud. So when you're provisioning cloud services, make sure that you're also thoroughly protecting the administrator account that has control over these services. So make sure that this is very, very clearly protected. And then use strong authentication for your cloud management control console. At least two-factor authentication and as thorough as possible. Cool. So we've covered hardware access control. We also want OS access control, so access control at the operating system level. The database, as I mentioned before, runs as a simple process in the operating system, owned by a certain operating system user, and this could be the name of the user, could be MySQL, Oracle, or whatnot. And when you list running processes for MySQL, it's going to be the MySQL user. This is the only user at the operating system level that is allowed to access the files of the database. So if you look at varlib MySQL, you see that there's the COM402 database, which is owned by MySQL and group MySQL. And this is the only user that is allowed to access this file, this directory, sorry. And the only user that can actually list files and change and modify things. So user management at the operating system level is so that only root, the main administrator, and the main MySQL user can access it. No other service or user running on this machine is allowed to access it. But from a security perspective, we're already relying on the access control mechanisms of the operating system to restrict access to the underlying files. Right, so the database needs these files to function. It stores all the private data in there. And we are relying on the operating system level for that. In addition to that, if we move up or down, depending on how we look at it, to the next level, we've got discretionary access control at the database. So the database uses discretionary access control to grant users access to objects. And objects in database parlance are tables and views. So there's different privileges. You can select information, as in you can list data in a database. You can insert, update, delete individual rows in a table. And you can create or drop tables, create new tables or drop existing tables. By default, root or system user has all privileges on all objects, which kind of makes sense because root can just delete the files and then your database is gone. Or raw hex edit the files, right? It's something you can consider. The database is just a nice visualization that implements access to the underlying files. But the root, the system administrator, always has raw system access. You can just open the database file in your favorite hex editor and then edit the file like that, right? So this is why root usually has access, because root already has access. Good? So for example, you would like to allow Alice to read, modify, or write name, address, and grades in the table students in this database. So we would add the grant as the administrator. We would execute grant, select, update, or insert name, address, and grade on COM402.students to Alice at localhost. Which means the user Alice at this address is allowed to modify the table by updating and inserting new information. How is grant implemented? Or what kind of data what kind of data structure do you use, or does the database use to store all user information? I've heard file system, I've heard table. What else? It uses a table, right? So in the end, this is just some syntactic sugar, or like grant is just some syntactic sugar on an insert statement on a very privileged table. MySQL as a database already implements the different functionalities to manage like these low-level tables and data types. So user management is best done through a privilege command that already accesses that part. So you simply insert into the privileges table to then work on that. If you want to give access at the row level, you can actually define views. So create view. A view is taking a subset of a table where you say year 2024 as select star from COM402.students where academic year equals 2024. And then we allow Bob to only read the lines as academic year 2024. Grant select on year 2024 to Bob at localhost. Right? So we can combine this control to have fine-grained access to each column and row of the database table. So SQL databases also support role-based access control, where you can create individual roles, which are created very much like users. Create role professor, grant select to all of these targets, grant update, blah, 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 where we just create a role professor with a certain amount of privileges, and then we turn me into professor that allows access to this local bit of information. You can then grant several roles to the same user. So this is role-based access control to just make things simpler if you're running a really large database, thereby distributing the load of it so that you can reuse this. Right? Remember, role-based access control from Monday allows you to break this up into a bunch of bits and pieces. Cool, so we've got this at the network level. Next up is network access control. Sometimes or often nowadays the application tier runs on this, sometimes the application runs on the same machine as the database. So the database can be configured to listen to connections only from localhost, so it's not being exposed to any network services or any network systems. In many other cases, the application tier runs on a different machine. So if you're a small company, you usually have one server that runs your database, your application, and whatnot. In most other cases, if you're reasonably sized, your database runs on a dedicated machine, and then you have a couple of caches and application layer machines that run the application logic. If this is separate, you need to be able to connect over the network, so the machine needs to expose a given port, and you can create, for example, user Bob that is sitting at this IP to have access to that by also specifying the password Bob has. In addition to that, we need to either install a firewall in front of the database using a local firewall on the database server, and or by restricting users to certain IPs. Right, so access control can be done at different levels. Which ones should you do? Which one should you do? These are three different ways. The database server, if it is not on the same machine, the database server needs to be configured to accept connections from the network. To limit the connections, we can either have a firewall in front of the database, have a firewall at the database server, or tell the database engine to only allow connections from certain IPs, for example. Which one do we do? Yeah? Mm-hmm. Cool. So you're bringing up an interesting point, right? The main point being security versus maintenance. Right? So ideally, from a security perspective, from purely security perspective, what do you do? All of them, right? From a maintenance perspective, you figure out what makes sense, what is maintainable. Because every time your system configuration changes, you may have to go through it again and change it and adjust it. Like it's going to cost you time. So you have to figure out what works. And then you figure out in your policy for the company, how likely am I being attacked versus what do I need to do to make this safe and secure. Last level is application level access control. Applications have their own layer of users and privileges. You're not logging into your application with a database user and database username. You also don't want to create a database user for every single user that you have. Now, from a security perspective, likely it would be safest to have one user for, like one database user for each customer that you have, but it's just not feasible. So usually an application uses a few database accounts to interact with the database. Right? An e-banking application has 1,000 customers in 3 tables, a customer table with all customers and their password hashes, an account table with all accounts and their owners, and a transaction table with all transactions and accounts. Access control is handled by the application through, for example, the customer table and then 2 other tables to find the accounts and give access to it. Now, there's a single database user to access the 3 tables holding customers' accounts and transactions. Application makes sure each customer only sees their own data, hopefully, even if the database user would have access to all the data. What are potential security flaws in this setup? What are potential issues? Yes, I stand by my by what I said.
Because if it does something bad, then if there's only one account and all of the application makes sure that you want people to see their own data, maybe in a month you will do wrong and things will go forward. If the application is now directly exposed to the users and to the outside, there are no more layers from
So a single user is not good because the privileges could spill to some extent, right? On one hand, privileges to other users, and potentially privileges to other parts of the system. Yeah, that's one part. Anything else that comes to mind? Is anybody still financing their studies through web application or web development? One? Huh?
The thing is here, if you manage to execute a query as the user which the application validates, the query executes its root kind of to the database. So if you can potentially have this SQL injection and do whatever you want.
Yeah, SQL injection could be challenging. True. Yep. So SQL injection is one of the issues that could happen. Also, a single user is going to be way too powerful. SQL injection, we're going to start with that. Pretty much means a lack of separating code and data. What does this mean? Right, we're communicating with the server, and we have one channel that is used for both commands and for sending data. So in the end, like we are not separating the code that we send and the data. An SQL command is essentially a program that we tell to the server, please run this program and then give us a result. But we're not just sending the program, but we're also sending data. Please run this program with these parameters, with this data, and then give me the result. So here it would be, I would run the program to select all names and grades from students where the name is, and here we give the parameter name in quotes. And it's like sending the source code over to the database server and then letting the database server run the statement, right? And here we've got, for example, param equals Peter or whatnot. Now an attacker could modify this request by filling out the form and saying parameter, like it's not Peter, but Peter single tick, union select name password from students, and then there's going to be a comment. Now this is a classic SQL injection where the name reads a bit weird, right, of the user, but if you paste this in here, the database would understand this as a command: select name, comma, grade from students where name equal single tick Peter close single tick, which in the program that is being interpreted by the database server finishes the parameter. Union, which selects and continues the program, select name from students, like fills in the other. And by the way, the rest of this line is a comment. Right? So this allows the database to then run the whole program, and will drop will actually allow the attacker to run an SQL injection. How can we get rid of this? What's a way to mitigate this potential issue? Does anybody know from another class?
We have to
Go ahead.
proceed to perimeter string and protect signs which can be counted as special signs.
You can clean up strings and validate them. What else? That's my third most preferred solution. What else? Yeah? That's my most preferred solution. What's my you can use prepare statements. We're going to see this in 1 second. What's my second most preferred solution?
Use regex to check for labels.
Regex?
Yeah.
I would tell the average programmer to avoid regular expressions as much as they can. That's pretty much the, like, it's a version of the third best solution. The second best is pretty much any framework has clean comments or clean ticks, like validate the string. So you could, if you don't have prepared statements, you can tell your framework that you're using, clean this string so that I can pass it as a parameter. And most frameworks have something like this. It's still error prone, not as error prone as cleaning the statements on your own. Why is cleaning the statements on your own or writing a regular expression so error prone?
It's not a good idea to clean it by your own. It's a good idea to find implemented in framework you're using. So it's fun. For example, if they have update of their syntax, they may have new exercise, and it's not a good idea. So you will just update your server and it will be vulnerable. It's better to use some built-in functions of your framework.
Oh, so you mentioned option 2, which is the built-in functions to clean up. But if you clean up yourself, the most common risk is that you will forget one. Here we have an example with single ticks and these comments. There's other comments that you can use, other special characters that you can use. And very likely if you implement your own, you're just going to forget some. Right? That's very, very common. Don't do this on your own. If you use existing functions in the framework, this is going to help and make this a bit better. But it's still going to be rather buggy because there's issues and there's going to be mismatches between different parts. So the simplest and best possible form is to just use prepared statements. So we're going to turn this into select name grade from students where name is %s. You know printf, right? In C programming. In printf, the very first argument is a format string, where you have some special placeholders. So you define all the placeholder, and you're saying the first placeholder here is a string, %s. And then you're passing an array, where you're saying in this first array it's just this string. Right? And that's a prepared statement. There's no way an attacker can send any command in this data, because this becomes data only. Right? The server knows that this is an array of data. And then it just walks through the different parameters that are being passed here and uses them whenever they are being needed or used. Okay, cool. Back to application level access control. Now we've discussed SQL injection. Now we're going to go back to the first answer that was given. Instead of using one single database user, we're going to spread the risk a bit. Right, so one database user with read access to the customer table, just for login purposes, so that you can do authentication, and the rest of it, in the rest of the application, you no longer need access to the customer table because you handle this through an authentication token that you save as the user with the active session. Then one database user with write access on the customer table for changing the user's password. You're only using this user in like one specific location in your application logic, thereby containing it to a very small piece of code. And one database user with read access on the account table, so customers cannot change ownership of accounts, but can just list the account information. And one database user with write access to the transaction table, where you can do the actual application. Right, so you have contained this pretty much, and each user will only be used in a small part of your application logic, allowing you to also contain faults. So if there's bugs in your application, this user is only going to use in one part of your application, this user in another part. So you've kind of contained it to somewhat least privileges. It's not exactly least privileges because you're still over-approximating across many different users, but it kind of reduces the impact of SQL injection and potential other attacks. Question?
How frequent are SQL injection vulnerabilities nowadays?
I think they're on the OWASP, they're top 3 at the moment. So, like one of the most common attack vectors. Yes?
Is this a general security principle? Like compartmentalizing access and rights?
Read and write, or compartmentalizing different components?
Access control, compartmentalizing access, or rights.
Yes, so you're as you're connecting the two different layers from the application logic to the database logic, you're separating the concerns. Instead of just having one database user, you're breaking this into different components. It's not just all of the database that is being exposed as one, but it's compartmentalized as individual bits and pieces. And if there's a bug in one piece, you only get access to that piece. Yes. Cool. Application level access control, right? So using different database users in application of the is an application of the defense in depth principle. Application implements fine-grained access control. The database implements coarse-grained access control. Now, if access control at the application level fails, the control at the level of the database still reduces the impact of an attack to some extent. And this is again a principle of multiple layers of security and a following defense in-depth strategy. Let's have a look at encrypting data and how we make sure to encrypt at the different levels of abstraction. And we essentially have 3 different levels of where and how we need to protect data. We've got yellow, blue, and purple. 3 main areas. Let me explain you the different areas, and that's mapping to what we've seen before, all the different layers that we've seen before. So we're mapping this to yellow at rest. This is data that is not moving, it's just being stored, while data is somewhere on disk or not being actively used. We've got data in motion as it is being transferred, as in it is moving, it's not being computed on, but it's moving from storage to somewhere else. Right? And we've got data in use. And for each of these 3 different scenarios, we have to come up with a way to actually protect the data by, for example, encrypting it. Right? So data can be encrypted when read or written to disk. The database can encrypt when reading or writing to or from a file. The database can encrypt when reading or writing to the network, for example, using TLS, transport layer security, as we discussed, or the application can encrypt when reading or writing to the database. Right? So, if the operating system encrypts the information before it is being flushed to the disk, this protects against somebody stealing the disk. If you're encrypting as is being written to a file, this may partially protect against the malicious operating system if you protect the database from the operating system. Otherwise, it gets the same benefit on the disk. For example, if a reason could be to encrypt at the database level if the underlying system does not support encrypted disks. So like this. At the network level, this is whenever data is being transferred back and forth. I already mentioned TLS. At the application level, if you don't trust the database itself. Right? So for example, if you do end-to-end encryption in Signal, the Signal application running on your phone will just store an encrypted message somewhere on the server to forward it to the other party without the server actually being able to read or access or act on your data. Let's now discuss all of these three different areas in a bit more detail. We're going to start with encrypting data at rest. Here, just as a definition, data that is stored on the server is data at rest. The operating system can encrypt the data before it is written to disks, which protects against theft or copy of the disks, and a user that can log into the machine and access the files of the database will see the actual clear text data, right? So this protects against somebody who powers down the system, grabs the disk, and then runs off. While the system is running, any user who can log in and has access to the files will get clear text access to the files. Okay? Databases can be configured to encrypt data before writing to a file. For example, the database, as it stores or dumps the information from the cache to the file, will just encrypt it using a key. And without access to a key, even somebody who has access to the files at the operating system level will not be able to read the clear text. Keys may be stored in local files or obtained from a key server, from different form of management services or whatnot. Most databases call this type of encryption transparent data encryption. Now, this doesn't protect against a malicious administrator because, how can an administrator get access to these files? Like, how does root get access to these files? If the database encrypts the files using a key that was received over the network while the database is running, the database encrypts the files and stays running to provide service. How can an attacker get, an attacker that has root privileges on the system, get access to them?
For example, you can track a network, and maybe if it's not transferred well, it can be caught. Or
Let's assume the network is safe.
okay, even he can just take it from raw memory with direct access from processes or
Right.
virtual.
Root is all powerful. If I am root, I stop the process that is running the database with a debugger, attach to it, and give a raw memory dump. Somewhere in this raw memory dump is the key to actually encrypt and decrypt the files. And this allows me to recover this key and then use it there. Here, an interesting question also becomes key management. One of the interesting use cases to encrypt data at rest is mobile phones. All right? And we've seen in the last couple of years a move towards full disk encryption for mobile phones and for laptops. And if you think about it, the phones are a type of device that you may lose somewhere. or like that may be stolen somewhere, right? Same as your laptop. Now, while a phone that is being stolen sucks because it's a couple of hundred Swiss francs to replace, what sucks even more is if an attacker would get access to all your private data, including your pictures, your messages, everything else. Like, I don't want somebody to have access to my photos, and I assume same for you. Now, the assumption until a couple of years ago was that if you have hardware access, like if you get hold of the phone, you have access to all the data. Now, since a couple of years, since the rise of mobile phones and lots of private data on these mobile phones, full disk encryption has gotten pretty versatile and ubiquitous. Right? All the phones, or I would say most of the phones today support full disk encryption. Now, full disk encryption is being done on the phones using extra hardware, trusted hardware that manages and stores your keys. Otherwise, if I have hardware access, remember we assume the attacker has hardware access, they could just take the chips. And when you're rebooting a phone, you have to store the keys somewhere to encrypt the disk and the different blocks on the disk, right? So this is usually done using a little bit of trusted hardware. This is also why you have to enter your PIN code every time you boot up the system. Like on Android, you can log in with biometrics in most of the cases, but you have to enter your PIN code whenever you reboot, because the PIN code is used to unlock the storage, the secure storage that's on the disk. Right? Otherwise, the fingerprint is stored on the secure storage. This is why you can't log in with the fingerprint. So encrypting data at rest is good. Next is encrypting data in motion. Data is exchanged in our running example, between the database and the application. If it's not encrypted, it could be eavesdropped. Most databases support TLS encryption for database connection. Pretty much straightforward. You slap on TLS, you communicate as you were communicating before, and TLS just gives you an encrypted channel from one end to the next. One thing that we do that is different from the web, you would usually do some form of certificate pinning. Right? The client can be given a copy of the server certificate or of its certificate authority. Right? For your application, you can just lock on the actual database that you are using by doing a 101 match. Now, this is different from the web, where you have to accept a very large amount of certificate authorities, which is the biggest threat on the web or for web security. Here, you know that this is your database. It's your database that you're connecting to. Therefore, you can actually lock towards it and then refuse connection if anything else is being presented. Right? So certificate pinning is that the client stores a hash of the certificate that it expects, or a list of hashes of certificates it expects. If it's not in this list, it will not be allowed. That means you pin it. Right? Anything except for these certificates will not be allowed. Encrypting data in use by the application. So with encryption at rest and in motion, data is still clear in the memory of the database. As we discussed before, an admin of the database server can dump the memory and see all the data. The solution would be to encrypt the data in the application before storing it in the database. Now the key is being moved from the database to the application tier, as the application holds the key. There's no way to decrypt the data on the database server. Now this brings up an interesting challenge. Right? What are the challenges, or what are the issues that we face if we actually, if data is encrypted at the application level and only stored in encrypted form in the database? Yeah?
If you lose the key, you lose the data?
If you lose the key, you lose the data. Yes, but this is true for all forms of encryption. Something specific to this situation.
Filtering or executing queries.
Say again?
Filtering and executing queries.
Yes. Can you expand? What's the issue with filtering?
If we want to use a certain filter, which is like string compilation, we cannot do that on encrypted data.
Yes. So we lose access to the database, loses access to the data. And what are database services? Right? For example, we want to look at certain values. We want to limit the selection that we have to certain numbers. We want to sort. Encryption will make sure that all of the data that is stored in a database looks roughly uniformly random, which sucks for sorting. And it's certainly, the encryption is certainly not order preserving. Right? So we can no longer sort, we can no longer select, we can no longer modify. So in the end, the database becomes a collection of just dumped data blobs. And everything else, all the functionality that the database used to provide needs to be pushed to the application level, which makes the application level much more complicated. The database cannot search, cannot sort, cannot compare, and makes the database useless, essentially. Now, it's not useful in general, but it's useful for certain information, such as credit card numbers, right? You may want to encode credit card numbers to make sure that if somebody steals the credit card information, right? If somebody steals your database, they don't have access to all the credit card information that is in the database. Same for PIN codes. You're perfectly fine decrypting the PIN code on the user side. What about passwords? Does it make sense to store passwords in encrypted form in the database? Who thinks yes? Who thinks no? We've got less than 10% response rate. This is terrible. Commit. Who says yes? We should store it encrypted. Got like 5, 10. Who says no? We should never store it encrypted. We're now to about 20 to 30% response rate. Still better. We're like at Swiss voting levels. Interesting side bits. Democracy is not about convincing other people. It's convincing your people to vote. Right? If you think about it, if 70% of people don't decide to vote, it's convincing the more people to go that are on your side already to go vote than the other way around. Convincing people, it does not work. It's a very sad lesson. Answer to this one, passwords.
Hash passwords?
We hash passwords, right? Never ever under any circumstances store passwords. There's no need for you to store passwords, even if you encrypt them, right? You don't want to store passwords, ever. Don't. Hash passwords, you don't need to encrypt them. So far, so good. So summary for database security. Data stored in the database is often the main asset of a company, both facing privacy and security risks. We learned about access control at the different levels, physical level, operating system, database, network, and application, with different trade-offs for all of these levels. The database can do both discretionary and role-based access control, where we looked at different examples, distributing this a bit. And encryption is an efficient way to protect data, transparent at the operating system and physical levels. Network traffic encryption is a must through TLS. Interestingly, even across data centers or in a data center. Why would you protect network traffic in a data center if you control it? Because in the end, TLS is just a little bit of overhead, right? It comes at a cost. Why would you still encrypt it at a database, at the data center level?
That's because network be tracked on the hardware level. So someone
If it's your network, do you care?
yeah, because if someone enters your data center with Ethernet cable with some microchip inside it, he can track all the traffic without any.
Yes. So this was, until 2010, people thought that this doesn't happen. The risk that this happens is so low that we don't care. Right? So it is a risk. It was somewhere on the risk catalog, right? People had it on the list. They, like when you do risk analysis and threat analysis, you actually list all the different risks that you face. And people just listed it and said, like, it's not going to happen. Very low risk. Right? And if you've got low risk, a couple of % performance cost. Like for something that is this low risk, it was considered that the performance cost was way too high. And people just didn't do it. Then the Snowden leaks came out, which showed that several governmental agencies had raw access implanted backdoors in server centers and also in fiber connections across data centers, because they dug out cables and they connected to these fiber cables. And since then, TLS is pretty much a must. Everywhere you, like any time you connect different servers, you just do TLS. So you no longer need to think about this. Especially because we saw that this risk or this threat was actively being exploited, we changed the standards. And it's security is similar to science in regard that if something is being shown, it needs to be re-evaluated and then adjusted. So we learned from this attack as a security community and have updated the standards. Last but not least, some data can be encrypted by the application itself, but then you may lose functionalities such as sorting, comparing, and whatnot. So far, so good. Passwords. I'm going to move to passwords a bit and talk about them. Storing passwords or storing data to compare passwords is important, but unfortunately, password leaks are also common, right? So here in this example, we have the collection number 1 data breach with, what is it? Like close to 800 million records of usernames and passwords, which is a fairly extensive record of information of accounts that have been compromised, collected across several data breaches that happen at different companies. Right? So these are usually extensive data collections. They're also rather common. So if I check, that was one of my one of my email addresses that I checked. Have I been pwned? Or you can check as well. Right. So my email address shows up in a bunch of leaks that has been there in the past. Question?
So you said passwords shouldn't be stored, but should be hashed.
Yes.
So these, for example, Apple does this keychain access system. Like other systems do that as well. Do they then hash the passwords, or are they stored?
Keychain is the password manager, right?
Yes. So any kind of password manager.
So password managers store the passwords.
Right.
But in an encrypted form, which is an interesting form, right? The encryption is not at the level of the company, like so the company cannot decrypt it, but the encryption is tied to your account. This is why you have a master password somewhere in your, like you should set a master password for your password manager, so that it stores and restricts access to the different passwords. Interesting point, right? So maybe countering the password sometimes should be stored. I did not differentiate between it, so thank you for bringing this up. So passwords can be stored if it is stored on encrypted on a per user basis. What I meant, like I generalized before, I said passwords should not be stored by the application, where the application logic has the rights to decrypt the passwords at one point in time. Hashes would not be enough. because logging into a web application, you need to transmit the password over to the login as part of the login procedure, right? So you wouldn't be able to log in into your services by just storing the hash. Yeah?
Maybe to generalize, you can say that the password of the current application should be stored. Because this becomes data for other services.
A web application should not store encrypted passwords somewhere. It's essentially a password manager that is running on your local system is somewhat of an exception because it multiplexes across all the different passwords. It takes one password to multiplex to hundreds of passwords. Right? So you're trusting the security of your hundreds of accounts to this one single password that is set in the password manager. Does that make sense? Cool. Now, but with things like have I been pwned, you can enter your email address, but I think it goes without saying that on all these websites, don't trust test your password website. Right? So this used to be a game as like test the strength of your password, and then it gives you a number from 1 to 10, how strong your password is. Entering your password on one of these websites is not a good idea because you're obviously transmitting your password to a third party. I would highly recommend against doing that. So yeah, password leaks are very common. There's like millions of email password pairs, thousands of different sources. There's massive lists, things that are being stored. In the end, I think it's a mix between password storage being really hard and people making the same mistakes again and again. Like I think in the break, several people asked me regarding SQL injection. Why is SQL injection still a thing now that we have prepared statements? Well, not everybody goes. There's no need for going through a computer science education to become a web application developer, right? You download software and you are a web application developer. You copy and paste 3 things from Stack Overflow, and you can sell your services as a senior web developer. Right, so you're very likely gonna remake the same mistakes again and again. But you who are going through these classes, you will spread the knowledge about how to handle secure password management, and you can do better. Yep.
Out of all of these email password pairs that are published, how many of them were hashed maybe badly, or maybe they were able to reverse?
What's a bad hash for you?
If you don't solve it.
Yep. Well, 10 years ago, salt was not standard. Right? So the password strengths or the recommendations evolve on how to handle passwords. Also, like some of my passwords that were leaked were hashed with MD5, which is no longer considered secure. So the standards change, but the leak remains. So there's a mix between people using, like, either storing passwords in plain text, that still happens fairly frequently, or using weak hash functions, that still happens frequently, or hash functions just getting out of date, because there's this trade-off between the cost of a hash function and the security it provides. And we're going to have a couple of slides on this in a bit. So the naive approach to storing password is plain text, right? Store password in clear text in the database. OOO web host, store passwords in clear text. That was then exploited to steal 30 million passwords. Never ever store password in clear text on this server. Better is hashing the password. But as I just mentioned before, right? Password hashes password hashing was done using weaker algorithms. Like Windows still uses in parts MD4 hashes. So almost all passwords of length 8 can be recovered in under a minute. Now, a classic way of mitigating the issue of like short passwords and reuse of the same password across multiple sites is to use salt and iterations. Like one of the issues we are facing is like humans only remember short passwords, simpler passwords, which very likely can be cracked fairly easily. So what do we do to make this harder to crack automatically? Like a brute force approach would be just trying all the different combinations, trying all the different letters, letter combinations and number combinations. A simple way would be to add some salt to it, which is a random string that is prepended to your password. And then as part of your account, you store username, hashed password, and the salt, right? The 3 different values. And every time the user enters their password, you take the salt, you append the password that the user entered, you hash it, and then you compare the hash. It's a very simple operation. Now this helps. Another approach would be to use a memory hard function. Cracking a password requires some memory. Specialized hardware with many computing cores, such as graphic cards and FPGA, do not have enough memory to speed up cracking. So 2 approaches to better passwords: salt and iterations, or memory hard functions. Let's dive into this a bit and see what the background of this is. First, importance of salt. Salt is key. It makes everything tastier. Old versions, for example, SMB version 1, did not salt their passwords, which resulted in interesting breaches even in the late 90s, where computing systems became powerful enough to break this. And what Microsoft didn't consider, likely when they shipped it, this was good enough, but then Moore's law caught up, and it was not future-proof enough to protect against ongoing attacks. I see somebody in the chat. Okay, somebody was speaking. Cool. Importance of salt. Yes, let's go into this. Salt, as I just mentioned before, random data concatenated as an additional input to the hash function. So instead of just hashing the passwords, doing h of password, you add this salt to it. And salt is just a random sequence of text. This can be like 16 random characters that just append to it. And then you obviously store the salt in addition to that. Now this makes cracking a password much harder, because your password just got 16 characters longer. So instead of breaking, instead of a brute force attack tries all the different combinations. Instead of trying all the different combinations of letters and characters, you now need to combine all the different letters, characters, special characters of the password plus the length of the hash. So it's making this much harder. That's benefit number 1. Benefit number 2 is the salt is different for each user, because you're storing the salt on a per user basis. So if user A and user B have the same password, the hash will be different, right? So that's the second benefit. WPA, WPA2 use the SSID as salt. You can also use something that you know, right? And then 4,000 iterations of HMAC SHA-1. Yes, please.
How do you know when you go back what part was salt and what was the password?
What do you mean when you go back?
When you want to use your password and you need to, do you know?
You don't care about the salt, right?
Yes,
It's just
how do I know does the system know what part is the salt? How does that work?
So the system the system. Let's say you change password. The system takes your password, generates a new random salt. So you're transmitting your password to the system, the application. The application takes your password, creates a random salt, let's say 8 characters. It takes the random 8 characters, appends your password.
Oh, just at the end.
Just at the end.
And hashes it then.
Yeah, and then hashes the concatenation of it. You just combine it together. and then you just store the hash, and you just need to remember if it was before or after.
Okay.
Right.
Thank you.
And then you store the hash and the salt in the database or somewhere, and then you're good to go. Cool. So yeah. This means that for both for these two, here you know the salt, right? Because this is the SSID, but this still allows you to crack part of the SSIDs. Yes.
I'm a bit confused about how the salt works. Like when you want to log in, you send your password.
Yes.
It adds the salt.
Yes.
And hashes it.
Yes.
What will stop a hacker from doing the same thing, sending your password, and then the system adds the salt and hashes it?
Yeah. Usually in a password leak, you have both the password, the hashes, and the salt.
I mean, I don't see what the salt adds to the security, because can't a malicious user just send your password without the salt and the system adds the salt?
Correct.
So
If the malicious user does not know your password, they need to go through a brute force attack. A brute force attack means trying all the combinations of all the letters and characters. Right? This is usually prohibitively expensive. Now, if you have access to the salt and the hash, you need to go through all the different combinations. And you need to do this for every single user. Usually if you have without hash, we're going to cover this in a bit, but without salt, if you have a list of hashes from a password leak, you go through all the letter combinations once, and then you look up, and then you can crack a lot of different accounts.
I see.
And with the salt, you need to do this on every single operation, for every single user.
Passwords longer.
It makes the password longer, so it becomes harder to guess. It also individualizes passwords on a per user basis. So you need to do this iteration for every single user. And it just increases cost.
How do you upgrade a system if you go to work at a company and they use the MD5 and you want to change that?
Yeah, you store what hash was being used, like MD5 was being used. Then you the next time the user logs in, you increment the version field after the password check, because MD5 returns true. You have the password, you hash the new version of the password, you update it. Or you force the user to update the password, telling them, hey, your password is out of date. Good question. Yes?
Salt is only useful if they get access to the database of the hash and password, or it changed something if the hacker wants to connect through the connection portal of whatever site.
I don't follow what the question is.
Okay, my question is if an attacker wants to connect to my Instagram account on the Instagram portal, it doesn't change anything. The difficulty is the same whether they store it with a salt or not.
By just trying multiple different passwords.
Yeah.
If you're trying multiple passwords on the Instagram website, it's the same.
Yeah, it's just
with the difference that very likely you're going to be blocked after 20 tries or so, right? But let's say somebody broke into into Instagram, downloaded all the passwords. They can try cracking it, and the salt helps against the cracking of the passwords. Yeah.
So, if I am an attacker, and we have one case where there is no salt, and one case where there is salt, you say that the case where there is salt makes it more computationally demanding to crack the password based on the hashed salt, the salted hash. Sorry.
I have slides on this. If I get to the slides, I will be able to answer this question.
Okay. Let's see the response.
Cool. Great questions. You're asking lots of things that will come. Bear with me for a bit, and if I don't answer the question, we can take it in the break. So some systems store the password as a simple hash, such as PV hash equals h password. Passwords are hashed without salt. There's two major weaknesses. That's what I tried explaining before. Multiple hashes can be cracked at once. Let's say you downloaded 1 million accounts, right? You broke into a server, you downloaded 1 million hashes or 1,000 hashes, and you want to find some, you want to find some of the passwords of the accounts. This is an important distinction, right? You don't want to find a particular password, you want to find some of the passwords. So, if you want to know if any of these systems has the password correct, horse, battery, staple, you calculate the hash, and then you look up the 1,000 hashes if any of them match. Right? So this means you need to iterate through the list of all the passwords, like all the passwords that can be generated. Like you start with AAAAAA, AAAAAB, AAAAAC, AAAAD, and you just keep iterating. You do the hash, you do a lookup, and sometimes one of them will match, multiple ones will match, and so on. But doing the hashing of the password, like going from password to hash, is the most expensive operation. Doing 1,000 comparison is O1, or at least constant, right? In big O notation. So it's a smart data structure. The lookup is almost free. So it's one hash operation. You can try cracking 1,000 passwords. So you're scaling out and can use this to test large data breaches. So cracking n passwords requires the same amount of hash operations as cracking one. Second, if you don't have salt, hashes can be calculated in advance. Let's say you want to create a list of all the hashes of 8 passwords, 8 characters. You can create all the different hashes ahead of time, create a big table, and then store this table. So some hashes, some passwords have no salt. Every user on the earth with password blah, 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 has the same hash, and you can just do a comparison. Now, if an attacker has enough memory, you can store the information of all the different hashes in a big table. Think of this as building a database of hashes that maps hash to password. Now, this requires a bit of storage. So for 8-byte characters plus digits, like upper, lower, and digits, this requires almost 5 petabytes, which is a bit much, right? I don't have that storage. But doing this for just digits is easy. For shorter passwords is easy. For just letters is easy. Or just characters and then one letter at the end is easy. As soon as you constrain the characters, this becomes much more feasible, right? The full set, doing this on a full set becomes kind of hard. So you cannot store the full table for all the passwords, but for some of the passwords. Now hashing gets rid of this, right? For hashing, this no longer becomes feasible because the password gets so much longer. Now let's spend 10 minutes on time-memory trade-offs. I hope I convinced you that storing this, all the different hashes, just becomes too expensive storage-wise. And we're discussing about solutions that trade off compute versus storage. Now, assuming we have no hash, right? We do this thought experiment for the next 10 minutes. Assuming we have no hash, we could pre-compute all the hashes and store it in a big database. Afterwards, each lookup becomes an O1 operation, right? Now this becomes a cheap operation, but then we need a lot of storage. Or every time we see a hash, we just compute all the hashes. So this becomes very cheap regarding memory, but very expensive regarding compute. So you're trading off compute and memory. And this was called a time-memory trade-off. That was already discussed in the 1980s by Martin Hellman. also Turing Award winner, to inverse cryptographic functions. When you double the memory, it's 4 times faster to invert the function. And it's pretty much what I meant, right? You're trading off time versus storage to some extent. So let's give an example for password cracking where we do such a time memory trade-off. So we trade more time of cracking a password for creating a smaller table. So instead of 5 petabytes, we want a somewhat smaller table and restrict the amount of information there. Our original table just has all the passwords and the hashes, right? So we store all the hashes, and then we can look up the actual password in the same row, right? So we pre-calculate all the hashes and passwords. It's all stored. We just go back. We know, but this requires a lot of storage. 24 bytes for the hash, plus 8, 16, 30 characters for the actual password. Memory is n times password length plus hash. Time of cracking a password is time of finding a hash, as in OC, or O1 for in simpler form. Now, can we fold this table to some extent? So number of passwords, there's still n passwords, and we want to halve this and just have 2 rows. By storing them somewhat in one row and not storing as much data in between. So we're turning this into some connection where we have password, hash, password, hash. Right? So we want to store a chain of passwords. Now the question is, how can we connect these 2 pairs? And this is where we introduce a reduction function. So we've got a password that was hashed to H0. Then we do a reduction function, which becomes password 7. We hash it, it becomes the hash of password 7. And then the trick is that we don't store this information in here. So we only store password 0 and hash 7. Okay? It's going to take 2 or 3 more steps, and then you're going to see how this actually connects. It's a very neat and very cool idea. My main question when this was explained for the first time, how does a reduction function look like? Well, a reduction function takes, a hash function takes as input a password, or like a string of text, and turns out a 24-byte hash. Okay? Reduction function takes as input a hash and returns a password. What password? Doesn't matter. Just a password. We can create arbitrary reduction functions. I'm not going to do this as a quiz, but just list it. So the reduction function glues the hash function of the previous computation to the current one. So it takes a hash and returns a password. Requirements is that the output follows an alphabet. Right? For example, the alphabet may be, like we're looking at all the passwords with lowercase letters, uppercase letters, and numbers up to 16 characters. So the reduction function should return a password in this alphabet. Right? Otherwise it doesn't make sense. Also it should have few collisions. Like we don't want that it always gives the same password. The password should be uniformly random to some extent, but deterministic. Which also gives you a hint of what a good reduction function is. Right? It's like a form of a random number generator, pseudo-random number generator. Output is reasonably uniformly distributed and doesn't require any specific structure. Let me walk through 2 examples. So we want to crack H1. We found password H1 in a leak somewhere. So we look up H1 in our table, H11. We find H11 at the end of this table here. So what we do is we go to password 2, we hash password 2, we get h2, we run the reduction function of h2, we get password 11. Right? So we've done this chain, right? We found h11 in this list, and we managed to go to the beginning here, and to figure out password 11, we have to just hash and reduce. Okay, now the big question is, how do we find any of the hashes in here that we don't know? Let's go through a second example. We want to find the password for h1. We don't find it in the table because we don't store it, right? So what do? If we don't store it, we run the reduction function and then hash it and then find it here. Now we know it's P1. Okay? It's extremely clever. Let me repeat, right? We want to find the password for h1. It's not in our data structure. But what we can do is we can run the reduction function, get to P64, hash it, get to H64, which is in our table, which gets us P1, and we know it's H1. Now there's only one more step. So time for cracking. The password is time of one reduction plus one hash plus finding a hash match. Okay? So we've saved half the space. Yes?
Can you do further reductions?
That's the only thing that's left. Right? So the trick here is you take a bunch of passwords, you store them, you hash them for a certain amount of time, and then you store the final hash. Now what you do is, if you find any of these final hashes, you just go to the beginning and run the reduction hash chain again until you find the corresponding password. Okay? That's very, very cool. If you're looking for any of the passwords here in this chain, which are not stored, right, because we're doing time memory trade-off, you do reduce, hash, reduce, hash, reduce, hash, reduce, hash until you have a hit. Like reduce, hash, lookup, reduce, hash, lookup, reduce, hash, lookup until you have a hit. And when you have a hit, you're good, right? Very cool. And this is how you store, like you pre-compute once, like you pay the computational cost of computing all the hashes once, and then you only need to store a very small subset of the table, of some initial passwords and some hashes. And to look up any of these in this table, you just go iterate through this table and you're good to go. So reduction functions may collide. That's one of the difficulties, which results in identical chains, right? So if the reduction functions collide, this results in an identical chain and wastes some time. So we can change this a bit and then have different reduction functions at different times to generalize this a bit using a trick for this operation, and then you just have to run multiple times until you hit the chain with the different reduction functions. So slight improvement. Let's take a break here. Do you have a question? Go ahead.
So the way you work is all the hashes arbitrary or
Say again?
the way you give numbers to each, like 0 and 7.
Here?
Yeah, is it like it goes from 0 to 0 to 7, is it arbitrary?
From here to here, you mean?
Like why don't you just go from 0 to 1?
Well, these are just random numbers for me. Right? It's just the reduction function that turns like P0, you hash P0, you get a hash, then you take the resulting hash, and turn this into a password, and it becomes a random password. But I cannot do all P question marks, right? So I had to give them some numbers.
Yeah, but the P7 that would be in the first row is different than
the P7 that is?
because it goes P, the left column there, the left column goes P0, P1, P3. It's not the same P7, right? You can know.
This one is not the same as?
As the one that would be in the like.
Yes, it's not the same. Now maybe as a summary, like there were a lot of questions. Sorry, a lot of questions regarding the. I'm going to use this as a break for the video when I cut it together. Lots of questions for the rainbow tables. Let me very quickly reiterate because there were lots and lots of questions. Like all the great part here, you don't know. The trick is to only storing the initial passwords and only storing the initial hashes. So what you're doing is to look up a hash, you reduce, you hash, you look up. You reduce, you hash, you look up until you have a match in the back. This gives you the row that the password is in. Then you restart on the row until you have a match of the hash. And at that point in time, you know what you put into the hash function previously, and you have recovered the password. Right? So you pre-compute this table once, and then you can use it to look up any kind of password. Now, this is a very, very cool trick to trade off some compute with on the order of thousands of hash functions versus 5 petabytes of storage. Right? This is a massive reduction of storage that you have here. Now, interestingly, using salt, you can make this technique ineffective. Because with a salt, the password gets so much larger or so much longer, and the alphabet used in a password gets so much more complex that it's no longer effective to use rainbow tables or any kind of these storage tables. So the salt is a random value that is added to the hash function to prevent cracking multiple hashes with a single calculation and pre-computing these hashes, because you would have to pre-compute the table for every single possible salt combination, which makes this just ineffective. Each user has a different random salt. We need to store both the hash and the salt in the database. When the user logs in, as I mentioned before, we use the salt to generate the hash and compare it to the stored hash. So what cryptographic primitive can we use to combine a salt with a hash, and how can we make it harder to crack? Now, how do we hash passwords? Like what's a good hash function? I think it's already answered. It's a bit of a not so great question. So we just concatenate salt and password and just go through a cryptographic hash function. How can we make it harder? We just repeat it. So instead of running hmac SHA-1 once, which may not be sufficient, we just define that to hash a password, we need to run it 5,000 times. Right? And then the output, the hash output, is just being fed into the hash function again 5,000 times, and then we just store the final result. This makes it harder for the attacker to compute the hashes and slows them down. Cryptographic hash functions are designed to be fast and simple to implement. Simple to implement is good because it allows us to verify their correctness. But also, modern graphic cards calculate, for example, hundreds of billions of hashes per second. So hashes have become fairly, or should I say, attackable using massive compute available in GPUs. A simple way of slowing down the attacker is just doing the hash function multiple times. 5,000 iterations will slow down the attacker from, will slow down the login from nothing to nothing, but it will slow down cracking from 4 hours to 2 years, right? Because you've got this cumulative factor in there for all the different passwords. Like, this makes this much more effective. Now, there are standards that define how you should, like how many iterations you should do. There's official standards for salt and number of iterations. There's the password-based key derivation function 2 definition, which is defined in RFC. That's used in Wi-Fi, Mac OS, user password, Linux disk encryption, and previously for Linux passwords. And for Linux passwords, this was SHA-512 with 5,000 iterations, which was considered reasonable enough, right? That's good, right? So it slows down, but with exponential increase in compute, this is going to become a bit more difficult to run. An alternative to just adding additional iterations are so-called memory hard hash functions, which instead of making it hard on compute, make it hard on memory by using a lot of additional memory. Yes?
What's the difference between the password cryptographic hash function and a normal hash function?
A cryptographic hash function is like HMAC SHA-1, for example, because it's going through SHA-1. Another hash function is shifting right and XORing with 15. Which is easy to reverse to some extent.
So basically you're hashing the password along with the...
Like a normal hash function is not uniformly distributed. Like if you look at the implementation of the hash function for Python or other languages, it's like 5 lines of code, very, very simple. A cryptographic hash function will make sure that this is uniformly random and low collisions and whatnot. A cryptographic hash function takes, let me guess, 10,000 instructions, whereas the Python hash function will take like 50 instructions. Make sense? So the cryptographic hash functions are usually implemented in taking all the bits, shuffling them, and then making sure that all the bits are spreading or distributed across all the bits evenly to some extent. Okay, so on to memory hard hash functions. Iterating a cryptographic hash function is not ideal to slow down an attacker because an attacker may just throw much more hardware at it, either specialized hardware or FPGAs. Graphic cards are used for 2 different approaches, either for, like, let's say 3 approaches. Few people use it for gaming. A lot of people use it to train their machine learning models. And the NSA buys billions of graphic cards to run them in their server center to crack crypto hashes for you. So it's not ideal to use just more iterations. Now, better password hash functions, instead of making it more intensive to compute, make it more expensive to run by using more memory. So for example, 16 megabytes of memory. For a single login operation, having 16 megabytes of memory is feasible, even on a small IoT system. But graphic cards or FPGAs usually have a couple of gigabytes of internal memory for thousands of parallel iterations. Right? So they are usually hit by this constraint. They don't have terabytes of memory to use this. So this makes this limits the usefulness of graphic cards by moving to memory hard functions. Memory hard functions, the idea is that you run through many steps. Intermediate results are stored in memory. So it's a lot of back and forth to main memory. Load, store, compute, load, store, compute. And each step depends on results from several previous steps. So you need to keep track of all the intermediate results and you keep adding to it. For like for cryptographic hash functions, it usually works as you only look at the last iteration and you keep iterating. For memory hard, you're going through all the different intermediate results and you just recombine them again and again. If you do not have enough memory, you can still calculate the result, but you have to recalculate intermediate values again and again, slowing down and reducing the benefit of this parallel approach even further. For memory hard functions, you can usually parameterize like how much memory it should need and the number of steps to calculate it from. Two well-known memory hard functions are scrypt, which has been standardized in 2016. The typical configuration uses about 16 megabytes of memory and around 100 milliseconds of compute. Or Argon 2, which was a winner of the recent, a recent competition to find new approaches. Now, if you benchmark cracking operations on a reasonable G-force, like if you use the Windows hash function, you have a couple of million hashes per second, like, which is terrible for password security. If you use SHA-512 crypt, this is what Linux used before, you've got a 370 kilo hashes per second. The OS X, 1,000 kilo hashes. Cisco with scrypt has like 40 kilo hashes per second, which shows you a bit of the differences in systems. So it's like an order of magnitude better than the current SHA-512 configuration on this somewhat powerful hardware. When implementing password storage, always use salt and make the hash function slow. Use YesScript, scrypt, or Argon if available. Otherwise, use the key derivation function too. Now on Linux, most systems have switched to YesScript, which is the memory hard function I just mentioned. Salt and hashes are stored in etc shadow, right? And like you know why. So Linux uses two files, and we've seen the first file on Monday, etc password, and the second file, etc shadow. And etc shadow contains just username and hashes. etc password contains all the users. etc password is world readable. Now, back in the good old days, etc password contained username, ID, and the hash of the password. But when password hashing started to become a thing, this was moved, the hashes were moved into shadow and hidden from all the users except for root. So it's like a defense in depth strategy, that the hashes were no longer accessible to the average user. Before, any user could read the hashes out of etc password. Now, you need to have access to etc shadow to drop the passwords. Now, the difference here is that we also need an additional, like a privileged command to compare the password. Before, you don't need special privileges to compare and read the hash. All right, so this has become a bit more complicated, but yeah. Now, what you see here is this is my username, $y$. Y tells us the type of the hash, which is YesScript. J9T is the configuration that we use. That's a parameter for the hash algorithm. This is the salt. Right? You see the salt is fairly extensive. And then here you've got the hash of my password. Good luck cracking it. Now, the parameter, like $1 would be MD5, Blowfish, SHA-256, SHA-512, YesScript, and none of those mean any of the old systems. Now, summary of password storage. Never store passwords in clear text. Right? Never do this. Always use salt to store the password. If you do not, multiple hashes can be cracked at once, and hashes can be calculated in advance. using something like a rainbow table. Salt is insufficient on modern hardware, must slow down the hash function as well, because you can still crack individual accounts. Therefore, iterations are a good start using PBKDF2, or memory hard functions are the best possible options for you to look at, such as YesScript, SScript, or Argon2. Cool. Let me spend 3 more slides on secure remote passwords. Just an idea that like if you exchange or validate passwords over the internet, the default approach is to send the password in clear text and then have the server validate it. But one option is to make sure that you can validate passwords without sharing this information. Secure Remote Password Protocol is a password authenticated key exchange, or PAKE, where you can exchange this information among the two parties. Password authenticated key exchange allows you to verify the password of a remote party and exchange a key for later encryption. In TLS, it's implemented as the server signs half of the Diffie-Hellman key exchange to prove possession of the private key, and thereby proving its identity. PAKE is similar, as it's based on Diffie-Hellman, but authentication is based on the password as key, where the server stores information about the password. So it can be cracked even if the attacker sees all the messages. Quick overview of this protocol. We're not going to go too much in depth. I'm just going to walk you through the steps. The protocol is like Diffie-Hellman with additional elements that depend on the password. So we've got a generator and a modulo for each user. Server stores username, salt, password verifier, which is the exponentiation of a salted hash password. Server adds V to its part of the Diffie-Hellman exchange and contributes to the calculation of the key, thereby validating the two sides back and forth. Alice asks for the salt of user U. Bob looks up salt, sends the salt. Alice calculates the password hash. Choose random A, choose random B. Then we run Diffie-Hellman, and essentially they both get the key, which also, as a side step, validates the two parties. We're not going too much into detail of the protocol. Just know that as one of the possible crypto protocols, you can use this to validate the two parties and also authenticate them. Alice and Bob have only exchanged public values. Eavesdropper cannot learn anything from those, and they cannot brute force the password. But they get the benefit of actually authenticating each other and checking that this actually, that they're actually validated. If a hacker takes control of Bob, they do not learn the password hash X, could try to brute force them from the exponentiation that they have. Before continuing, they should of course send each other an encrypted message or a MAC to prove that they succeeded in calculating the key, thereby validating that the protocol, the exchange protocol, has successfully completed. Let me summarize. Data security touches 3 kinds of data. We've covered a fair bit of information this class, combining different aspects from the previous 2 classes. Data security looks at data at rest, in transit, and in use, and we need different kind of primitives for all these different types of data. As we are walking through the different layers, the data must be protected through all of them, from the hardware at the lowest level to the application on top and to the user management. Never store passwords in clear text. Always store hashes. Hashing with a salt is key. Ideally, or even better, if you use a memory hard function or lots of repetitions as a fallback. And with the PAKE protocol as an example, remote password authentication allows authentication without leaking passwords. That's all for today. Thank you for staying with me. I will stick around for some more questions that you have. If not, we'll see you on Monday for the quiz. The quiz is going to be at 4:15, 16:15 in CO01. Materials are the first three classes, OX01, OX02, and OX03, not this class. Cool. Thank you.